Welcome back. So this is a bit comparator. You could see a 3-bit comparator. This is a very simple code. In fact, you could see in your Morris Mano, a different logical gate level structure would have been given. You can also write in the structural level coding, but this is a data flow style where not data flow style, yeah, data flow where maximum 3 lines is quite enough to write a code for a comparator. But you can check only 3 options: greater than, less than, or both are equal to. So you can even cross check this, go here and simulate and check it out. So what we have done is, the idea is only simple. A, B are my input. So I have given 3 outputs like A greater than B, A less than B, A equal to B. So again, these 3 outputs has been assigned something like this using a relational operator. When A is greater than B, then this signal will get 1. If it is less than, then this signal will get enabled, or it will get 1. If both are equal, then this will get enabled. That's all. So that's how it has been arranged. You can go here and do the comparator. Okay. Right click, add to waveform, selected signal. So let me give input for these two. So I'm giving 1011 to be the A. B is 1010. So let's try to simulate this one. So A is greater than B, so that's what you get the first signal. Let me change this as 0011. Then I need to get the other one. Yeah, this get as 1, the other goes to 0. If at all, if I make this also to be 0011, then you could get the equal to. Yes, this getting enabled. So that's how you can keep on going through. So let me stop all this combinational sequential circuit time being. Let's go with how to write a test bench. That's what the next important thing, right? So first of all, let's quickly see what is a test bench, why do we need a test bench, and how to write a test bench. Yes. So basically, you made a CUT. People generally call that as a CUT. CUT cut means circuit under test. So or design, sorry, or DUT, design under test. So after finishing, say suppose you made a half adder, AB, sum and carry. Now I want to test this. What is the usual way which we are trying to do? I am forcibly giving some value of A and B and checking whether sum is equal to so and so, carry is equal to so and so. But the reality is, I am not verifying all possible combination of my input. So starting from 0, 0, 0, 1, 1, 0, or for multiple combinations, I'm not trying it. So just to make sure, otherwise, because sometimes your logic may work for few combinations and it may not work for few other combination. That's more dangerous because um, if certain operation which has not been exercised for a particular input condition, if that could create a problem on the user side, then the complete IC need to be replaced. So if you fail to verify this in the design phase, it will cause a huge loss after manufacturing. So that's what you call it as a verification. Though it is called as a testing, there is a slight difference between testing and verification. Testing is being done after an IC is being manufactured. Functional verification is being done after you freeze your design, or before freezing your design. You keep on looking for all possible combination of your input and then check your output. Strictly, the program which you write for test bench, no way relevant to design. This is my design. This is my test bench. Actually, the test bench is simply to force a value to your design and check your output. Other than that, it doesn't have any role to play. Or you are not going to synthesize this test bench to make an equivalent hardware. That's why we say in test bench, you can write all the constructs which are not synthesizable, right? Whereas those constructs are the commands which are written in the test bench, which is non-synthesizable, should not be used in the design. If you are using so, while you give this design, because the design need to be synthesized, whereas test bench need not be synthesized, or it will not be synthesized. Okay, right, that's all. So your test bench is merely another program which uh, may or may not have the port list, which is mainly used for testing the design by giving in a set of input combinations and visualizing your test output. That's what our whole idea, right? And in the design, we followed one methodology, that is, we deliberately said all our input should be a wire and output can be a wire or be a ridge. Now, for a test bench module definition, the thing whichever you have defined that as a wire should be declared as a ridge, because from this test bench you are going to feed in value for A and B where it need to store now. It is getting the value. So all this wire which has been declared as wire in input for the design need to be declared as a ridge. All those ridge need to be declared as a wire because that is required to be connected to the output for visualizing it. That's the main change. So module, you can give a module name, same idea. You can have a port list or you need not even have a port list. Go there and define your input output as usual. Then call, instantiate your design inside this test bench, because you are supposed to use this design under test, and for this design under test, say full adder, I am calling full adder F1 with all the corresponding port list. After this, mainly you use two statements, that is always and the other one initial. The main difference I have said yesterday, can someone recollect? What is the difference between always and initial. Can someone? Come on, come on, come on. No answer?
Initial will run only once, while always every time there's a change in value.
Very good. Right. So always runs n number of time, means based upon the sensitivity list. Even it can be without sensitivity list also. It keeps on running n number of time. When it comes to initial, this anything inside this initial will run only once. So by default, what you need to do, whenever you want to initialize some value, so initialize count equal to 0, you can put it over here. But when I say clock, definition of a clock, that need to come with inside this always block. Why? Say, let me write like this. After 5 unit, I failed to say this. Hash 5 indicate it is a delay for 5 unit of time, or this instruction will get executed only after 5 unit of time. Hash 5 clock equal to tilt of clock. So what does this mean? If it is entering in this always loop, first of all, I initialize clock equal to 0. So first it will be 0. After 5 unit of time, the clock is assigned with the tilt of clock. What does this mean? It will go to 1. How long it will be there? It will be there for 5 minutes, 5 unit of time. Again, after 5 unit of time, what is happening? It is again tilting. Like this, you will get a continuous clock. This is a clock generation module. A simple, a 2-line statement will do this. One initial block, one always block. The first initial block, you put it at the top, make our initialize clock equal to 0. From there on, put an always block, inside an always block, after 5 unit of time, so invert the clock. So you will get a continuous clock. What would happen if I put this statement inside this initial? Can someone give the answer? Instead of putting that inside the always, I am putting inside the initial.
Conditional. If condition is happen, then event will happen. Always n times.
No, my question is very simple. I am removing the statement from there and putting it inside the initial block. So what will be my output?
It will be constant. Clock signal will be constant.
Clock signal will be constant. Any other answer? Any other? Come on, just now we have discussed. Still the answer is not right. Okay, in case if I am moving this inside an initial statement, that's the reason I said very clearly, an initial block will execute only once. So what will happen? First you will have 0. Then after that, if you give this statement over here, after 5 unit of time, it will get inverted. So you will get clock only for one clock cycle with a time period of 10. After that, it will not repeat it, because an initial statement will get executed only once. Since I have kept inside this always, right, it keeps on repeating. Whereas in the initial, only at the starting point you want to make that as 0, only once. So I am putting the clock equal to 0 and inside this initial, and inside the always I am putting like you can decide what should be the frequency of operation. You can give hash 10 or whatever you require. That's fine, right? So if your design require clock, make sure you are putting inside the always block, and you include one initial block for initializing the clock. Then say suppose comparator, you put another initial block. Inside this block you give value for a, say 0, b 1, whatever. Then after 10 unit of time, so this happens at 0, like 1. After 10 unit of time delay, you make a equal to 1, b equal to 0. Then after 10 unit of time, you can keep on giving all possible combination in the test bench. And when you start running this, you will get the output for every time delay whatever you are given there. This input will be forced on. You can monitor that also using one command. This is system task command. This is $monitor. Monitor is to display the output for every unit of time you will get, whereas display you will get only at the last, whereas $monitor, it will give you whenever there is a change in the input that will get printed in your transcript window. That's all. So as such, now we have seen what is a test bench. Basically, test bench is used to test your design. Apart from that, it doesn't have any role in your design, and it cannot be synthesized. There are some statements which is very specifically used inside the test bench alone, like initial, $display, $monitor, all those things which cannot get synthesized in the design, but they will be used only for the design test bench. And you can generate a clock, all those things can be done. So what you need to do is, one important point is convert all input as reg. The input in your design get as reg declaration, the output will get as wire declaration. Then you instantiate your design, and then using an initial block you appropriately give all possible combination of your input. Using the $monitor command, you can uh, display all the values of your output whenever there is a change in the input happening. So very simple code we have written for the mux. Let's try to see this. Look at here, module, and the module name is mux case underscore design, sorry, test. So this test bench is for, yesterday we have seen how to construct a design for mux, how to write a code for mux using case statement. For that we have made a test bench. Now look at here, these are my inputs A, B, S in my design. So now they have been declared as a reg, and the output was a wire or it could be a reg, but now you need to declare that as a wire. That's all. Now I am calling this, look at here, mux case M1. Now I am port mapping by name. It's not port mapping by order. What I am saying here is, in your design you have used A, so that the dot A is being connected with the capital A in my test bench. And similarly, dot B in your, I mean B signal in your design is being associated with capital B in my test bench, or it is like this. This is my mux. So let me assume that this is A, B, yes, I believe these are the signals being used. Now on top of this you have a test bench. This is design under test. Now this has capital A which is being connected to A, capital B connected to this, capital S, I believe I have given that as capital S, like this, capital Y which has been connected to this Y. That's what we are describing here. Yes, small for port mapping by name you need to use dot a capital A, like this. I'm port mapping everything as it is. And It doesn't require any clock, so I have not included any clock here. Initial, begin, and remember, inside an initial statement, you always need to have a begin and end, then alone that block get executed within that. So begin, dollar monitor. So the general syntax is dollar monitor within quote. So whatever you are typing, that will get displayed in the transcript. So sim times, that is simulation time, equal to, up to this point you will get as it is. Then percentage G will type or give this value, that is dollar time. This is again a compiler directive. Whenever this dollar time is given, it will print the current system time at this place, at dollar, not dollar, percentage G. Then A equal to, this will get printed, this percentage B for percentage, okay, B represent binary value. Percentage B binary, this binary is nothing but this A value. Similarly, B percentage B, again binary value of, it's very similar to your C comments, right? Again, this is binary value. The B value will be printed over here. And again, this select line, but make sure that these things should be capital letter, because that is the signal which you have defined, right? The percentage Y, again, all these are binary values. So I have listed them one by one by using a comma in this. That's a very simple. And again, use one more initial. One initial block is used for monitoring, displaying, and one initial block is for feeding the input. So after 5 unit of time, I'm giving A equal to 0, B equal to 0, S equal to 0, another 5 unit of time. Why this time delay need to be given? Because it takes some amount of time for execution, right? So that's the reason I'm giving some unit of time delay between two subsequent value feed in. So again, you can keep on going ahead with all possible combinations, end up here and end module. That's all. It's a very simple test bench which which can be written. In case if there exists a clock, you need to define your clock also, as I have shown you earlier. In fact, we will see one clock generation program also. Now let me run this test bench. Go here. So once you have .v file of design and the test bench, you need not force anything. Go here, start simulation, mux case test. Yeah, this is the one. What is this? I'm getting something like, are you seeing some arrow in my screen?
Yes, sir.
I don't know why I'm getting like that. Okay, right. Someone can access my screen? Okay, right. So these are my inputs A, B, S, and Y. I'm just selecting and feeding that to select signal. Now only thing is I need to run as it is. Yeah. So you run that. Yes. Now the thing is, all the 4 value here itself. I think within 20 to 25 unit of time, picosecond we have completed that, because we are given 5 unit of time. So I think 4 or 5 input has been given. So all possible combination of 0 0 1 0 1 0 0 1 and 1 0 has been given. In fact, you can extend that for the first 5 unit of time delay, it is not working. That's what we are given the first unit only after 5 unit of time delay. That's why you get this red line, right? So then appropriately you are getting the input, output. So you could see whenever, let me assume here, if 0 has been selected, the value of select line is 0, the value of A will be passed on to output Y. So you are getting Y to be equal to 1. Say let's consider some other case. If select line is 1, the B value need to be passed on, 0 will be passed on to the output. So it's perfectly working fine. That's all about your test bench. So I think we have covered test bench 2. One more, let's see the clock generation network alone. If you see that, then you can be sure how to generate a clock. Yes, clock gen. This is a very simple program to generate your clock. In fact, you can make according to your need, you can alter that also. So module clock gen, output I am making the right output as clock. It doesn't have any input as such. Initial value is begin. I am giving one tick binary 0. Remember, this is not synthesizable. Right? Okay, it's merely a test bench, right? Always begin after 5 unit of time, clock equal to tick clock, end module. So you can just see whether the clock get generated with a time period of 10 unit of time. So you can go ahead. So that's what 2 blocks I have used. One always initial block, one always block. Go here, start simulation, clock gen. Okay, here comes the clock. Right click, um, add to wave, selected signal. Now you start simulating it. Now you can also see what's the time period. So from this point to this point, or this point is nothing but 10. So 5 unit of time for on period, off period. So this is 10 and this is 2 number of clock cycle. So it keeps on get generated. So whenever you run for what amount of time, here by default I have kept 100 picoseconds. So it will run for 100 picoseconds. For every click, it will run for 100 picoseconds. That's all. So that's all. We have seen almost the major portion of that, but still we have one more important thing, that's our FSM. So I will go with FSM, some of the ideas about FSM. Then after that, there ends. Yes, I'm. Of course, in this I have not covered some of the task, function, and all. They are not that much important, so I have skipped out. Otherwise, for any initial programmer who would like to start writing a program, this is more than sufficient. Only thing is the amount of time which you spend for writing the code, that will make you an expert. Yes. So I believe this is again one of the important topic. But what happens is sometimes most of the people who teach us digital, they spend more time as we did now with the combinational circuit, and while they come towards the end, um, they find the lack of time, then generally they don't focus much on this FSM. But remember, all digital design in VLSI or whatever, it involves FSM design. And remember, and again, this is quite easy. Modeling an FSM is that easy because the code template is a standard template. Only thing, the real toughness comes in developing that FSM model, right? So FSM, it's a finite state machine. Like, see, suppose I would like to come up with an FSM for ticket vending machine in the railway ticket vending machine. So you can look at all possible combinations. The point is, if I receive, let me assume that the ticket is ₹5. Now, this is the machine. You have been provided with a slot to put the coin here. Now, if at all the person having ₹1, he can first give ₹1. If he is giving one input, ₹1. Initially reset, it will be at 0. If he gives ₹1, then he will go to the state 1. One more rupee, he will go to the state 2. One more rupee 3. One more rupee 4. One more rupee 5. Now he is expected to, or the machine is expected to give the ticket. For all the other cases, it should not issue the ticket. I am just telling you how an FSM is being developed. If a person gives only ₹1 and the next he doesn't give any amount, then if he gives only 0, there is no input from him, then it need to come back to the original state by rejecting the coin after a particular amount of time. Then he has given only 2 input, ₹2. He didn't give beyond that. Then also you should not issue the ticket. Get back to the reset, that is in this state, without any issuing ticket. Fourth, except the 5, right? You are not supposed to issue the ticket, right? In case if the person gives, let me assume that ₹10, right? ₹10. Then the possible combination is you should issue a ticket in this, and I need to change the FSM slightly higher, right? What I need to do is first check, right, whether the coin is a ₹5 coin or a ₹10 coin. If it is a ₹10 coin, then the moment you receive a coin of ₹10, I need to issue a ticket and give a balance of 5 also. Appropriately, you give a signal to the actuator to give back the ₹5. Okay, the person is not giving ₹5, ₹10, ₹1. He is giving, okay, straight away he gives ₹5. Let me look into that condition also. If he gives ₹5 coin, you can straight away go to this state, issue a coin, issue a ticket, and get back to the original state. Okay, the person is not giving ₹5, but he has ₹2. Then what you need to do? When he first insert ₹2, you need to go to this state. Second ₹2, you need to go to this state, and another ₹2 you cannot accommodate here. You need to come up with one more state diagram, where this state diagram he has acquired 6. which means he need to give 1 rupee balance and issue a ticket. And then for the next clock cycle, he need to come to the reset. Okay, that fellow is not giving like this. He is giving like 1 rupee. Now you need to go like this. When it recognizes that it is 2 rupee, you need to come here. Another 2 rupee, you need to come here. Another 1 more rupee, you need to come to this particular state and give ticket. Okay, he is not giving like this 2, 2, 1. Instead, he give 1, 2, 2. Then you need to alter your state diagram. You see why I'm saying the wild possibility of making a state diagram. Even if you miss a single condition in the programming, right? If you fail to consider a proper state, then that will become disastrous at the user side. So if you are giving 1, so first you need to go here, and next you need to come to this state, next you need to come to this state. This is for a simple coin vending, ticket vending machine at a railway station I am speaking about. Still I have ruled out many cases where you may not take into consideration. Sometimes some people have a round which is not even being a coin. So those signal what you need to do. Under that case, so every new condition should be declared as a state, different state. And you need to say what should happen in each and every state. So this happens not only there, a simple lift if you consider, then you could realize the need for the FSM. Let me assume there are 2 lifts, 15 floors. Now you think about the possibility condition. An entering person can press first floor, second floor, third floor. So if a person, so first you need to have all the 15 floors. So where the particular the person press, when the door opens, when the door closes. So if you try to develop that for a single lift, that itself will be a very big finite state mission. In addition, in some places you would have seen, there will be a common pressing button for 2 lift. I mean, when someone coming here, if they want to go up, they will press this button. So anything which comes first should take up this passenger. So it need to check internally what is the location of that lift and this lift. Whichever lift comes first, that need to take care. And when someone pressing at the floor 7 to come down, and simultaneously one more person is pressing at the 8th floor to go up, then you think what should be the complexity involved, which need to be given preference, and what allocation should be given to these 2 lift. So it's like a massive task of coming up with a finite state mission. So as far as coding is concerned, the coding is a standard template, but arriving a finite state mission, that too effective finite state mission, means with minimum number of states, is the real challenge. Why I say minimum number of finite state mission, more the number of state you put in, more the number of flip-flop you are going to have, more will be the power consumption, as well as your resources required. So as a VLSI engineer, you will always try to see that wherever possible, you need to reduce the state without compromising anything on the unforeseen condition. So you should possibly look at all possible condition, at the same time without any wastage of extra states. This is what while you go with the books, they say that state reduction. You would have done that as a state reduction. And one more thing, more the state switching that takes place, that will lead to more power loss. Let me give you a simple example. Let me have 3 states, 4 states, let me assume. So this is 0 0 state. There are 2 flip-flops, 0 0 0 1 1 0 1 1. Remember, if you have n number of states, all the state bits should be unique. Let's assume that there is a frequent transition from this state to this state. So what is happening? Every time you switch over from this state to this state, there is a continuous toggling of 2 bit. That is 0 0 changes to 1 1. What is the matter in this? It is not going to be very serious issue. No, it's a serious issue with respect to power consumption. More the toggling will lead to more amount of power consumption. That's what you could read in your low power consumption, right? Power dissipation equal to C V square alpha into F, where alpha refers to the switching activity. So now the person who writes code should also be aware of what should be the assignment of states. How to code the state should also be known to him, right? So it is not the matter of coding here, because I will show you shortly how the template look like. That remains very simple, but the real challenge lies in coding or developing an FSM with efficient and minimum number of states, and coding that states with appropriate uh, encoders. Like you can follow something like binary coding techniques, gray code technique, one hot encoding technique. Like this, you can have multiple coding style. So based upon the need, there are many papers in this also which has been published. You can also cross refer. And in a book, some books also discuss, particularly if you go with the low power IC design, uh, how to design an FSM with which will give me the low power consumption. That idea itself is a separate discussion. So with this, let's get into this FSM. So FSM, there are 2 ways to code. Once you finalize the total number of state and its corresponding transition, I can code them using 2 ways. One is Mealy machine, the other one Moore's machine. Basically, for all this, you need 3: current state, next state, output. These are the 3, right? Current state is the state which is available in a memory. I believe you know what is a sequential circuit, right? Now it is something like this: a combo logic, right? You take the output, put it in a register or a memory, take this and give it back to the combo logic and give your input. This is my input, and this is your next state. Sometime the next state will be a memory state, or it could be an output also. So a sequential circuit is a simple combo logic added with a memory, means it is capable of storing what has happened in the previous. So if you give that as an input, so this gives an idea what was the earlier state, what is the present input. Based upon these 2, you get an output. That is the sequential circuit. If it is a combo logic, simply the output depends only on the present input. It need not think what was, say, suppose I'm asking you to add 3 plus 5. Will you ask what was the previous input? Definitely you won't ask. You will simply say 3 plus 5 is 8. And the other way, I'm asking a counter is counting the total number of people who has already entered. So I'm asking what is the next count. Then immediately you will ask me what is the present count. Already it is 5. If someone comes, then it is 6. There you need an information regarding what was my previous state. So whenever a memory type of thing required, you need a circuit which could take care of the previous one and the present one. Their logic which you design here should be able to give your output at the next state. So that's all. With this idea, again, I'm coming here. The next state or the output combo logic in a Mealy machine depends upon the present input and the previous output. Can you see here? The output is nothing but the present state. This is my present state that has been stored in a register that has been plugged into this combo logic. Combo logic is mere gates. So present input and the previous state or the previous combo logic output, they do combine with these two and give my output. And when it comes to Moore's machine, the next state depends on the present input and the previous state, whereas the output depends only on this present state. It is not taking, you see, this is an output combination logic. It is taking only this present state alone. I mean, the state which is being the output. It is not taking the input here. The output doesn't depend upon the input. Are you following me? So what you could notice here is the output is a function of, in a Moore's machine, function of the current state, whereas in the Mealy machine, it is the dependent on the output also depend upon the present input and the previous output. The next state depends upon the present input and the previous output. Got it? So that's what it says. The Mealy machine, the next state and the output depends upon the present state. By present state, I mean this one. Present state and the input, whereas Moore's machine depends on the present state. The next state depends on, this is my next state. The next state depends upon input and the present state, but the output depends only on the present state. This is my present state, right? How to write the code? Yes, there are three things in this, as I said: a state, input symbol, number of states, and the transition. So these are my state, these are my transitions. This will happen while you give 0 or 1 and that particular state. Now, how to model this, or what are the things required? One, memory element to store the current state. Next state, combo logic. This is my combo logic. Output state, you require a combo logic, right? So here output depends upon the current state or the current state and the input. This is for Mealy machine. This is for Moore's machine. When it comes to next state, it's a purely combinational logic. The next state, you can produce the next state by knowing the current state and the input. For both Mealy and Moore's machine, in order to give the next state, you definitely need to know the current state and the input. The difference is, in a Moore's machine, the output depends only on the present state, that is current state. Whereas in a Mealy machine, it needs the input also into consideration. That's all. So the current state is being stored in the flip-flop. The number of flip-flop required depends upon the number of state. So if I'm having 2 flip-flop, I can go with 4 different states starting from 0, 0, 0, 1, 1, 0, 1, 1. If I'm having 3, 2 raised to the power of 3 number of states, I can go ahead. So the same idea has been said over here. I'm just quickly moving out. Okay. One way, by seeing the FSM itself, you can say whether it is a Mealy machine or Morse machine. Right. Now look at here. In Mealy machine, what is the Mealy machine we said? Output depends upon present state and input. So see this slash value, no, these are my output. So this is the present state. If I give 0, I will get 1. So say it is moving from here to the arrow indicates from this point to this point. So the present state is state S2. If I give, it's like this. Input slash output. This is present state. This is the next state. Understood? For Mealy machine, if I am doing like this, state S1 to S2, when I give 1, it gives me the output 0 in the state S1. If I give the input S1, it gives me an output of 0 and move to the state S2. Could you understand? So if I want to say this one, current state is S0. If I give input is 0, the output will be 1 and it will be in the same state. If I am giving input to be 1, it goes to the state S1 by giving the output as 1. So whenever an FSM, the transition is being represented by input and output, then it is a Mealy machine representation. Rather, if it is a Morse machine representation, it goes like this. You will have in the transition like this. Say S1, S2, this is the transition. Transition will have only the input. You don't have output there because the output depends upon the present state. So the output will be represented here because this is the present state. It may be 0 or 1, whatever. So if I give input 1, it go to the next state S2, and in that current state it gives the value of 1, not during the transition, because my output depends upon the current state alone. Got my point? So whenever the transition has only one value, then it is Morse machine. Coding style, you can follow 3 coding style. You can use 3 always block, one defining current state, one defining output logic, one defining the next state. The second style is, some people use 2 always block. They combine the next state and output in a single always block and a separate always block for the current state. Some people follow still more another way, 2 always block. One always block is for combining current state and the next state logic, and you can even use assign statement itself. You can use assign to get the output logic. That's all. So here 1 always, 1 assign, 2 assign, 3 assign. Or you can even combine this, instead of 3 assign, 2 assign plus 1, 2 always plus 1 assign statement. This could make it, right? That's what it has been said here. This is coding style, separate current state, next state logic, output logic. I think that is being missing here. Now this style is, look at here. This is current state plus next state. You have in 1, and the next state and the output logic in 1 more always block. So here, always at passage of the clock, whatever the next state is there, that will be given to the current state. Now, in the next state and the output, I use 1 more always block. In this, this coding style, we will be using two always block. That's all. So here what is happening is either the current state or the in, you put the current state in case statement. So based upon the value S0, S1, S2, S3, you can define what should be your next value. So if it is, if the in value is IN0, then the next value will be I1. If it is a Mealy machine, you can define the output there itself. If it is Moore's machine, then you can define it at the last using an assign statement. So again, coding, I have said efficiency, all those things. Yeah, I'm stopping here. In fact, I have also given one sequence detector. I'll just show there. With that, we will wind up. So here we have used two always block. One always block is for converting the next state to the current state. Another always block is for assigning the output to the state. So y equal to 0, 1, all those things. And one more always block. This is three always block. This is for defining what should be the next state. So this is the initial. I said no, you can use three always block. One always block for the next state, one always block for the current state, and one more always block for the output. So this style of coding I have used. You can even use parameter to define the four state, which is used for detecting sequence detector. Yes. Now with this, I am winding up. Of course, you can still spend some more time on FSM, but for want of time, I am not in a position to do. Maybe you can just go through this, and if you have any doubt later on, you can just contact. And one more point which I would like to stress here is I have just shown the first stage of digital system design, because here following this you need to do synthesis with the Xilinx tool. I have not shown. Probably if there exists a chance, then I may be doing one more workshop on completely FPGA based synthesis, how to calculate the area, power, timing, slices, all those things. But that will also be somewhere over a 2 days workshop. If it is there, if it is planned, then I will let you know by including one target device. I have already one FPGA with high end. It cost around 2.7 lakhs, which I bought last year for my project. So if time permits, we will be putting that as one workshop, which is completely not on front end writing code, which will be only on the back end, like um, how to synthesize, how to analyze, partition placement, routing, how to get the power, how to get the timing, all those things. Let's see. If you have any doubt, now I can take a couple of questions. And then, otherwise, already it's time up to more than 40 minutes. Yes, couple of questions, I can take it up. No question then? Oh, okay. I don't know. If there is any question, then you can just post me. As I said, my mail ID, all those things.
No,
Yeah, yeah. Go ahead. You have something to ask? Yeah, I'm just writing my mail ID over here. R SAKTHIBEL @vat.ac.in. Okay. 4627570. In this, I'll be there in the WhatsApp. Okay, fine. So thanks for providing such a wonderful opportunity. Though the time was very less, within that we have made to the maximum extent what we could. Kumarasamy, Kumarasamy, if someone is there.
Sir,
Yeah.
can you provide us the material, sir, where you have discussed?
Separately, I cannot because some of the things are with respect to corporate things, but I could still I can provide.
Thank you.
செந்தில் முடிஞ்சிருச்சு. நீங்க எப்படி வரீங்களா இல்ல நானே முடிச்சிட்டுமா? Okay, fine. Okay. Okay, thank you. So some of the material which have been used for Wipro training, so I may not be sharing that one, but otherwise I can share some of the material which is already available in the net. But
Thank
you
you.
have sufficient material in the net, you can use it. This material
Thank you.
I'm just using for Wipro training for their employees, so I cannot share that one. Otherwise,
Fine, sir. Okay, sir.
all the other things you can go ahead. Okay. So
Thank
anything
you.
else? Okay, thank you. Thanks for joining. Have a nice day. Thanks for joining with me for these 2 days. See you. Bye.
Thank you,
Okay.
sir. Thank you so much, sir.
Thank you. I will stop sharing.
Thank you.
Thank you all.